Yes, so I'm Sharup from SINP. I joined SINP in about 1.5 years or so. So I'm still building up my lab that would mostly focus on microspectroscopy of two-dimensional materials, like the materials he talked about. But I do not really have something to show from SINP itself. So the result that I'm going to show are entirely from my postdoctoral works. Okay. So the presentation is titled as Excitonic Signatures of 2D Ferroelectrics, and I have used 3 different adjectives to categorize the ferroelectricity. One is sliding, the other is interfacial, and of course the honorary moire. So the first part of my presentation would mostly focus on what are the relevance of these adjectives in context of the emerging ferroelectricity that I'm going to show. And in the second part, I will talk about that how we can probe this ferroelectricity doing spectroscopy. So a brief introduction to ferroelectricity itself is that ferroelectricity is the classical analog of, or electrostatic analog of ferromagnetism. So here we have, so over here we have a electric dipole, and in this example, the blue and the red colored atoms, they are practically displaced with respect to each other, creating a dipole moment. Now, having the dipole moment is not just enough. You need to have the switchability application for it, that when you apply an electric field, it should switch the dipole moment. Then only it is a ferroelectric, otherwise it's a polar semiconductor. Now, the question occurs that where are the necessary degrees of freedom in a 2D material to host out-of-plane ferroelectricity? What I meant to say is, even if you have an out-of-plane dipole moment, how do you switch the dipole moment? Because strictly speaking, there is no motion in the out-of-plane direction. So that is question number 1. Second is that in nature, what happens, most of the ferroelectrics, they are insulators. Because the moment you have additional electrons or holes, they go and screen the dipole moment. So conductivity and ferroelectricity, they are 2 mutually exclusive phenomena just on classical scale. Okay? I would show you, without giving you the reasoning, that these new systems, they defy this classical limitation, or at least broaden the boundary quite a bit. Okay? So with that, then I switch to what we are actually doing. Basically, the material of our choice is the TMDs, okay? But not the usual polytypes. I mean, when you are doing exfoliation, in most of the cases, you are taking the polytype that is known as 2H, but the polytype of our interest is what is known as 3R, the rhombohedral stacking, or in other words, the ABC stacking, okay? In this stacking, the successive layers, they are parallel with respect to each other, unlike the 2H where they are anti-parallel. So why they are parallel? You see, if you look at these triangular bonds, the stretched triangular bond, they are facing in the same direction. So that is why I'm calling them parallel. And in this parallel stacking, the rhombohedral stacking, they neither have inversion symmetry nor they have the mirror symmetry. It's irrespective of either it's a odd layer or even layer material. And where does the symmetry break? You see, if you take the metal atoms of the bottom layer, in this case the purple colored atoms, it is eclipsed directly by the chalcogen atoms on top. However, the metal atom of the top does not have a chalcogen underneath. So this is where the broken symmetry is. Why it matters? Is because the chalcogen or sulfur selenide has much higher electron affinity compared to these metals, that moly and tungsten, and as a result, in this particular stacking order, that is what I named as MX, that is metal eclipsed by X, MX, it is also known as AB. So in this particular stacking, the top layer would gather some of the electron. So therefore, the top layer would become slightly negative and the bottom layer would remain slightly positive. And this is the origin of a permanent dipole moment or a spontaneous dipole moment. And needless to say that when you take this crystal, flip it around, I can name it as XM or BA, whatever you like. In this case, the ordering of the dipole moment has flipped. Okay? So we do have a spontaneous polarization and we do have 2 configurations as well. But the question is, how do we switch from one to another? So what happens is that when you take this crystal and subject it to an external electric field, like placing it in a parallel plate capacitor, they slide with respect to each other. And they slide in a manner that you have once the XM configuration and the other you have the MX configuration. So it is the in-plane sliding of the layers. It is the in-plane degrees of freedom of the layers that gives you a switchability in the out-of-plane direction. And it is this mechanism, the sliding of the layers, that's why it is known as the sliding ferroelectrics. Why it is called interfacial ferroelectrics is because the charge transfer that I mentioned, this charge transfer only happens at the interface. It does not, in other words, go to the bulk of the material. So it does not really go and sit around the MO or sulfur or whatever. It remains only at the interface. That's why it is known as interfacial ferroelectrics. We have experimental and theoretical proof for it, but that's for some other day. Now, the problem that when we started working on it, the problem is that there is no good way to get these 3R MOS2 crystals or 3R TMDs in general. So we adhere to this famous tear and stack technique, where you look for a pretty large flake, you break it into half and stack onto itself without too much of mechanical perturbation. And we hope that these two layers, they are parallel with respect to each other. And once we prepare our sample in this fashion, so once we are done with that, we measured the surface potential using KPFM. And this is how the KPFM map look like. Okay? So now the question is that what is this surface map is about? Why there are so many triangles, and most importantly, where is the information of ferroelectricity in this map? So the explanation goes as that when you take two crystals and do this artificial tear and stack, they are never too parallel with respect to each other. They would always have this finite twist angle leading to this moire pattern. We have been introduced to this moire many a times in this session on the previous day, so I will not go into that. Now, if I lock this artificial tear and stack layer at a particular twist angle, you see that there is this hexagon. I cannot really see it from this distance, but probably you would be able to see that there is this hexagonal moire symmetry, and like any other hexagon, you can subdivide it into successive triangles. And now, if the twist angle is low enough, then the atoms within this triangular regime, they will rearrange themselves in order to get into perfect parallel configurations. Or in other words, in one domain, the atoms would readjust themselves to get into this MX configuration or the MAB configuration, and in the next, they will get into XM or the BA configuration. So all of these triangles, they are ferroelectric, but in one triangle, the ferroelectric field in this picture is pointing outwards, and in the other, it is pointing inwards the screen. And it is this change in the dipole moment from one domain to another that has been picked up by the KPFM, and that is what the contrast is about. So this is why it is known as moire, and this is in fact is one of the beautiful technique to visualize moire. And all of these are room temperature measurements, unlike most of the moire phenomena that need 30 millikelvin, and with one more millikelvin down you get a new physics. So unlike that, it is a very robust room temperature phenomena that you can realize quite easily than others. And now we can actually make field effect devices out of it and keep on scanning the same region over and over again with varying the gate voltage. And we see that the contrast between the bright and the dark domains, that is the measurement of the strength of ferroelectricity, it remained roughly a constant with a doping level of about 10 to the power 13 per centimeter square. So this is what we claimed, that the ferroelectricity and conductivity, they can coincide in this kind of material. But of course, the emergence of ferroelectricity is quite generic to MOS2, MOSE2, WS2, WSE2. But this limit, that up to which doping level they would sustain, it is very specific to the material and what kind of doping we are doing. If you are interested, we can discuss in detail. Yep. But that was kind of the story when I moved to Germany, and the question that we had in mind that all of this ferroelectricity that people are observing were probed by some sort of near probe measurements. Either it be KPFM, conducting AFM, PFM, you name it, and you have some mapping of the ferroelectricity. But our question was, can this ferroelectricity be probed with some other degrees of freedom? I mean, take the word degrees of freedom a bit colloquially. What I try to say is that, is this ferroelectricity coupled to any other property, for example, transport, optical spectroscopy, spin value index, and stuff like that? And we also got, I mean, the motivation was of course this fundamental question, but it was also backed by the development in the field, that by the time I was there, one of the company, the HQ Graphene, they can make these 3R crystals now. So you can buy these ferroelectric bulk crystals and exfoliate them down to monolayer, bilayer, whatever you want. Therefore, we do not really need to make these samples in tear and stack process anymore. So why it is important? Because ideally then we can have larger domains, because usually in MORE the domain size is pretty low compared to the optical resolution that usually any far field optics can provide. And then the experiment of our choice was white light reflectance. We have later seen this kind of phenomena in everything, in PL, in Raman, and every other spectroscopy that is there. Okay, now this is the white light reflectance spectra. We have this famous A exciton and B exciton feature, and we know that this A exciton and B excitons, they are layer localized exciton. No many how many layers are there. I mean, nonetheless, how many layers are there? The exciton, the electrons and holes would always be residing on the same layer. Okay, they do not have therefore any out of plane dipole moment, any spontaneous out of plane dipole moment. On the other hand, we can actually probe this indirect transition by choosing the HBN thickness in a way, and then we can see what is known as the hybrid exciton, the gamma Q exciton. And over here the hole is confined to one of the layer, but the electron is distributed in the entire stack. Therefore, these excitons, they have both in plane and out of plane dipole moment. And therefore, what we anticipated from classical electrostatic is that this exciton that has an out of plane dipole moment would be coupled to the out of plane ferroelectric field, simple P dot E. And this exciton should not have any coupling to the electric field, because here the E dot P is 0. Okay? So let's see how it goes. This is the sample. I do KPFM, and you see this is topographically the same area, this area. But in KPFM you have a contrast. So this contrast is coming because these are two ferroelectric domains. Okay? What is the exact stacking order? I am not going into that, but these are two ferroelectric domains. Now the idea was, can I probe this ferroelectric domain by means of spectroscopy? What we did, we take this feature and mapped the intensity over the entire scan area, and we see there is no domain resolution in this map. All they care about is the topographical steps and all these things. So not quite what we anticipated, but later we focused on the A exciton. We also did the same in the B exciton case as well, and we immediately see that there is a ferroelectric domain just where we see it in the KPFM. So this was one of the experimental proof that this ferroelectricity can indeed be probed by spectroscopic measurement. This data was taken at 4 Kelvin, nominal 4 Kelvin, maybe the temperature is somewhat like 8 to 9 Kelvin. But we have experimental data where we can map the same at room temperature from room temperature spectral information. Okay? So with that, then we thought of why not we now, since now we can map the domains, let's see what else can we do with that. So we take a similar sample, and again we map field, we create these field effect devices and perform the same experiment, the white light reflectance on the field effect device. You see, in the central panel, when there is no voltage applied, I can already see a few domains. They are false colored in orange and Turkish, blue if you wish. Now when I change the gate voltage, this orange colored domain, it shrinks in size at the expense of the blue colored domain. So this is very much similar, that how a domain would shrink or increase in size in the presence of an external field. I mean, similar to any magnetic material or ferroelectric material. But this experiment gives us a hint that the sliding mechanism that I initially showed was not quite right. The layers, they do not slide with respect to each other, but it is the domain wall that moves. It is only the domain wall that moves, and the atoms close to the domain wall, they readjust themselves to get into this mx to xm configuration as a function of the gate voltage. And we have more proof for that, is that if I now put my spot, the white light spot, close to the boundary and do this experiment, the reflectivity as a function of external voltage, we see that they trace out this nice, very nice hysteresis loop, very similar to the MH loop or the PE loop of a ferroelectric material. And what is interesting is that this switching, it is very, very fast. I mean, we had a spot size of something like 1 micron, and within this 1 micron, remember it's a 3-layer sample, so we had 2 interfaces, and we immediately see that there is 2 sudden jumps. So there is, you keep on applying an electric field, almost nothing happens, and then all of a sudden there is a sudden jump. I mean, the actual data is even more dense. I have just taken out some to give you a hint of that. So we cannot really capture this jump. This is so sudden in a sense. And we have one more jump, so interface 1, interface 2, and when you come back, you again have interface 2 and interface 1. But of course, we have seen that if you keep on doing this experiment, these sharp transitions, they kind of keep on vanishing. They does not really become sharp anymore, and they smears out. Okay, so we believe that this domains wall, they start getting pinned to local defects and all the contaminations that are there. So this is about steady state spectroscopy. We have done time resolved spectroscopy, as I said, that spin valley and stuff. So what we can do is this 2-color pump probe experiment, where we can simultaneously measure the carrier lifetime and the carrier lifetime. Very standard setup, where we can take this A- for the expert. I mean, for the carrier, we do this A minus B. We make another home built circuit to measure the A plus B, put it another lock-in, and then we can simultaneously measure carrier and lifetime. This is what we do. And the rest of the setup is kind of very standard. And this is the experimental scheme that I will not go into. And now here are the results. You have 2 domains. Here I cannot really map. I can just put my pump probe in particular spots. So I have done the experiment once in domain 1 and another time in domain 2. So you see, irrespective of where I am doing this measurement, my exciton lifetime, these are all excitons, the exciton lifetimes are kind of very large, irrespective of which domain I am in. Okay? This goes up to something like 100 picoseconds. On the other hand, when I look into the carrier signal, the spin lifetime of the excitons, in one domain, the lifetime is about 15 to 20 picoseconds. However, in the other, this vanishes as early as it gets. I mean, it is very close to the temporal resolution that we have. Okay? So after 2 years after this publication, we still don't know why this happens. Maybe we need some more theory about it, but maybe it is the out of plane ferroelectric field that is generating some sort of SOC that we're not very sure of. But yeah, with that, then I first of all thank you all to listening to me. It was pretty quick. Yeah, okay. Okay, whatever it is. So I would like to thank Moshe. The work was done in Tel Aviv University with Moshe Ben Shalom. We got theoretical support from Oded and Lior of Weizmann. Of course, everybody is getting HBN from Taniguchi and Watnable. I worked with the spectroscopy part was done with Tobias. Got support from various funding agencies. Humboldt was one of them funding my fellowship. Some fellowship, some project funding during my postdoc, and of course, all these guys, the funding agencies. Thank you.
Thank you for the very interesting talk. So, session is open for questions.
Yes, of course.
Any hand-waving arguments for your lifetimes?
Not really. We thought of putting some, but not really. Maybe some Rashba or something because of the electric field. But on the other hand, this cannot be argued too strongly until and unless I know that what exactly these stackings are, because that I don't mention, is that these are all 5-layer samples. Okay, so in 5-layer you have 4 interfaces. Now each interfaces can take up polarization or down polarization. So there are something like 16 configuration of domains that I can have in this sample. Okay, in this 5-layer sample. So it's something like 2 to the power n minus 1, where n is the layer number of interfaces. Okay. And out of that, I only have 2 interfaces. So I do not really know what is the total ferroelectricity or total field in it. Okay. And until and unless we know that, putting an argument would not be quite strong.
Is the pump power low enough for trusting these?
Yes, yes. These are something like 50 microwatt for the pump, and probe was something like 10 microwatt per centimeter square. Something like that. Yeah, focused. Yeah. No, it's not focused. The power was the nominal power in a power meter. No, it was not focused.
50 microwatt per centimeter.
50 microwatt was the power, and 50 microwatt was focused on. No, it's not centimeter square. Yes. No. Sorry.
Focused.
Yes. Focused. Yes. Yeah. Okay.
Hi sir, yeah, very nice sir. So I just want to know from code, when you perform the KPFM and reflectance, has it been done in same time together? Because
No.
the KPFM
No. KPFM was done in an AFM, commercial AFM, park systems, if you wish, and the spectroscopy was homemade spectroscopy thing. Yeah.
Then how do you compare those areas, like the domains, what you compare?
Because of the size, because of the overall structure and everything. Because it's the same sample. I mean, finding out the same sample is not difficult. It is the same flake and everything. I mean, for example, if you want to have a look. So this is a optical micrograph image, and you see there is this topography step. This is a 5-layer sample. This is a 7-layer sample, and you have a step. And this is where the step is in KPFM. This is also where you have the optical contrast. I mean, the reflected contrast between 5 and 7 layers. So I mean, we have no doubt that it's the same spot that you are measuring, and once we know that it's.
Thank you.
So how did you get the 3R configuration? It was by just putting one layer on top.
In this sample?
Yeah.
No, we bought it from HQ Graphene, and they are selling this 3R MOS2.
And in this particular spectra, how can you show that the thing that you get at 1.7 is not a defect-related emission?
You mean over here?
Yeah.
Yes. First of all, we see it at room temperature as well. This is one. The second, usually the defect transitions, they do not have very high oscillator strength to show up them reflectance, right? Usually we see it in luminescence experiments. So that is 2. And second is that there is a conventional redshift as we keep on increasing the thickness. So all these 5-layer peaks, they are at a higher energy compared to the 7-layer. So yes. Usually this is not there in any arbitrary sample, but we choose, depending on our silicon oxide, we choose the HBN in a manner such that this peak appears a bit more prominently. If you take some other HBN where the sample looks like purple, like the cover of the seeds, you would not see this feature. You would only see this A and B. Yeah.
This is Mukesh. Nice talk.
I cannot, yes. Yes.
Nice talk. Optical contrast, you cannot see any difference, right? But when you get it, yeah.
Yes, yes. Yes, of course, because these are all same samples. Okay, these are all MOS2 on top of MOS2 on top of MOS2. So the difference between these stackings are let me, since I have a lot of time, maybe I can show that to you. So the domains that you see, so in one domain, first of all, I don't know what the exact stacking are. There are 16 different stacking, okay? But let's take just 2 examples. So in one domain, it can be this. So you see, if in every stacking, the chalcogen is slightly lower than the previous. This chalcogen is somewhat in this side, in this side, in this side, and that, okay? So these are 5 layers. All these interfaces, the polarization is pointing from left to right. But in one domain, one of the layers has slided a bit more. For example, this fourth domain, this layer has just, instead of coming down, it has gone up. Instead of coming down, the chalcogen, instead of coming down, it has gone up. And then they have followed the same trend. The chalcogen is gone down. Okay. So you see, all of these are 5-layer MOS2. Therefore, we do not nominally see any change in contrast, but of course the measurement I'm also doing, that is also optical contrast. So if our optical microscope have that resolution, we would probably see a change in color, but usually we do not. Yeah. Yes. Over here, yes.
Yeah. Sorry, I don't know if you mentioned this. Did you do second harmonic generation?
No, no. But not in these measurements, but when we first bought this 3R MOS2, we were kind of skeptical that is it at all 3R. So the experiment that we did was the second harmonic generation, and we get this, is it a n square dependence or n dependence with thickness, something like that, instead of this odd and even oscillation. So we do know that it's 3R.
Okay, then I'm a little confused. So you're saying the stacking 1 and stacking 2 are both still 3R stacking?
It is still rhombohedral stacking. I would not necessarily not put the 3 in it, because 3 is a measure of how many repetition you have in bulk. So I would call it a rhombohedral stacking, R stacking. You are not convinced?
I'm a little confused.
Yeah?
I wouldn't say I'm
Okay.
because I would expect if the stacking, if you have a natural bulk crystal, this stacking would just persist.
Yes, it does.
Whereas there could be 2 different stackings within the same bulk crystal. Is that what you're saying?
Yes, yes. Usually it does, but we induce this stacking while, first of all, there can be domains because of screw dislocations and all in the bulk itself. On top of that, we induce these domains while we are transferring. In the paper with Tobias, in the supplementary, we have done an experiment that when we are stacking this thing, like the typical 2D transfer, and we usually have this 1 or 2 domains, very big 1 or 2 domains. But now in one stacking, what we did, we have shaken the thing while stacking, and immediately you will see that you would have this moire-like ferroelectric domains all over. Okay, so it is so we are inducing the sliding by putting this additional mechanical energy to the system. So why there are domains? The answer is there are twofold. That during the growth there may be some screw dislocations, and during our preparation of the sample we may have induced one.
So one question from my side.
Yes.
This role of substrate on the domain dimensions of the switching, is there any direct evidence of this?
On the role of substrate on the formation of domain, there is no experimental proof, but I would not suspect it, that if there are any role in domain formation. But of course, the substrate would certainly play a role in the switching capability. If the surface is rough and contains a lot of contaminations, I would say the switching would be more difficult. But if we have a clean substrate, and therefore sometimes we do not top encapsulate it with HBN, because we have a feeling that when it is encapsulated from both sides, the switching becomes a bit harder. But again, people have shown switching in both structures. So I think it would also, this 2D transfer is also very subjective to how the labs are doing it, right? So something like that.